Hello everyone, I'm back with explaining another important paper. Today I want to talk about the mHC, manifold con- uh, constrained hyper-connections, which is an important paper from Deepseek. They released it last day of 2025, and in this paper they solve one of the big problems with hyperconnections. I will start with some introduction and history of uh, hyperconnection. Then I will go and try to explain what is the manifold constrained hyperconnections. So historically speaking, we had the residual connections which came in 2016 by introduction of ResNet. In this architecture, we had two flow of information. One directly go without any layer or anything in between, and then we had another which go through some functions like if and through such layer, and then go to the next layer. Uh, and however, this architecture changed a bit during the time. The main idea stayed same between different architectures, such as convolutional attention mechanism and feed-forward networks. And it was a paradigm until 2024, which hyperconnection was introduced. We had these two flow of information uh, because the first one, which is the identity mapping, do some important things for us. Firstly, it brings stability, and secondly, it will ensure that our model will not uh, explode. Also, it will increase the efficiency in the larger scale trainings. Uh, we can formalize such architecture as uh, x of L, which is the uh, input of layer L equal to x of the previous layer uh, plus some uh, sorry some function of this x of L and the weight of uh, that layer, which is this function here. And when we have it through multiple layers, it will be similarly x of L plus the sum of all these layers, f of x of I and the weight of that specific layer. It's nothing new. We all know it from almost a decade. But there were several problems with this architecture, including that it was not super efficient, and people started to think about how we can make it more efficient. That's why in 2024, a group from China, the Zhu group, if I pronounce their name right, from Seed Foundation model team, they introduced the uh, hyperconnection architecture. Uh, there are several differences between this architecture and the residual connection. Again, we have these two flow of information, but we have some hyperconnection functions. what does this hyperconnection do? What it does is that we have here this XL, which has the dimension of C and N, which sees the dimensionality of one of them, and we have it through N inputs. The HC transfer this to one single matrix with the dimensionality of C, then pass it through the function of X, and then return it through the okay, post, I don't know why it's post mapping connection. Why we do this learnable mapping aggregation from NC dimension to C dimension and again back to NC? It's important because it can increase the efficiency of our model, but it increased the instability of it at the same time. So it's some positive things about it and some negative things about it. So we were not sure how we can make this both at the same time efficient and stable until manifold constrained HC. What else? Yeah, the main concern was the instability, and also they didn't talk about the memory efficiency, so that was also another concern, or maybe something that it's always technically important when you want to train your model and do some hands-on things. If you want to go back to paper and see how they explain it mathematically, it's each layer is the hyperconnection res of the previous input, plus some post hyperconnection of the function, which is same as the function in residual connection, but we here we also have the pre-hyperconnection and the weight of that layer. So basically this is the this one, and this is this one, and here we also have the res mapping. So we need to talk about the drawbacks of hyperconnections, then we'll go to the mHC architecture. As I said, the main drawback was that it was not stable, and they demonstrate this in their paper with several indexes. First one is the absolute loss gap, which basically is the loss of the method minus the loss of reference. Reference here is the mHC, and the method is the HC. And when they said it's absolute, means that it's absolute value of this thing, which doesn't make sense because here it went even lower than 0, but if it's absolute value, it should not. So I'm not sure how they calculate it, but they show that it's not stable. It fluctuates a lot, and most of the time this gap is huge, which means that during the training we don't have a, a stable loss function. And another thing that shows that HC is not as stable as we want is the grade norm, which is a magnitude of the gradient, which again shows how stable is our model. Basically, HC let the gradient by multiply by arbitrary matrices, and mHC force it to behave like an identity on an average. Another thing that shows the instability of HC is the Amax gain magnitude, which is the index that they introduced. And in the forward process, it's the maximum of the sum of the row of our matrices, and in the backward process is the maximizing of the column, which basically when it goes higher, it shows the higher instability. On the other hand, MHC, with some tricks that I will talk about them later, try to fix them in a narrow range and doesn't let the signal to noise ratio to go high. Sorry, to go down. And another thing that was a problem of HC was the GPU memory efficiency, which, as you may know, is one of the most important thing, as modern GPUs have much more flops. The computation usually is not the bottleneck, but the GPU memory is. And it's very obvious that with lots of hyperconnection learnable matrices, we will have significantly higher memory cost, which demonstrate here and shows how much it needs per each of the layers that we have. All right. With this, I will go finally to the mHC architecture and talk about their solution to the problems that we just talked about. The main idea is very, very similar to the hyperconnection. So basically, we have two flow of information. One is this path, and the other one is going through the pre and post mapping path. The difference is that here we start with a normalization. So basically, we again have this input in n layers. Then for parallelization, make a vector of XL. Then we have the root mean square layer normalization. Then then we have three different flow of information. First one is going through the hyperbolic function. Then have one alpha, which basically try to get rid of small values. Basically, it's gating. And then we have, and it's of course learnable. And then we have a learnable bias for each of them. And then each of the hyperconnections of pre, post, and res has some function. For the pre and post, we use the sigmoid function, and for res, they used synchron knop algorithm, which basically is their main creativity. But what is the synchron knop algorithm? If I pronounce their name right, the idea is that if we have matrices like this, we want to transfer it to a doubly stochastic matrix, which means that we want three rules. First one, sum of each row should be between 0 and 1. Second one is that sum of each column should be between 0 and 1. And the third one is that none of the values can be negative, so all positive. And how this algorithm works is that iteratively it starts from a column and divide it by sum of start from a row divided by sum of the row, and so we will have sum of 1 in this row, then do same for the column and continue it until the values doesn't change much. Here they used 20 iteration, but of course that's a value that you can change based on how much computation you want to have. So with this, I think we know the architecture now and their innovation. Now we can go to the result. So firstly, they calculate the absolute loss gap. Here the baseline is a vanilla transformer with residual connections. And as you can see, mHC performed the best. Then they compared the gradient norm, which as you can see, the baseline had these crazy jumps, and HC was completely unstable, going everywhere. But mHC performed very good, and it was decreasing very smoothly, not vanishing, not exploding, and that's exactly what we wanted. Then they compared them from some benchmark perspective. They saw that basically mHC performed the best almost in all of them, in several math, reasoning, and knowledge, and so on benchmarks. And they also show that the Amax gain magnitude was very good, as we expect from a double stochastic matrix. It should be very smooth, and it should be around 1 all the time. And they show that it's exactly what's happening. Same for the forward and backward process. So again, it shows that it's relatively stable and can learn very well. Then they visualize the learnable mapping. Here you can see that the real magic happens here, while the HC explode have super high or super low values for its columns and rows, and it can destroy the signal and add lots of noise. And the mHC keep it always around 1, and simply by iterating 20 times through the algorithm. So it's not computationally much more expensive, but still it can be ensured that it's stable. With this, I'm done with this paper. Please make sure that you subscribe, because in the next video I will go through the code and try to implement mHC. And if you like the video, I would be happy if you like it, share it with your friends, and see you next time.